Thank you all for coming. Welcome to discussion hour. Today we're going to have another one of our group research highlights. So we're going to hear from Sean Gulick and his group. And the way we did this last time was basically everyone in the group had a certain amount of time to talk about what they're up to. We had some time for questions in the meantime. You guys have a lot of folks, so I don't know if you want to if you felt differently about the timing.
We'll just run through it.
Okay, excellent. So we'll have some time at the end for discussion about what everyone's up to. But other than that, I'll let everyone introduce themselves as you go along, and it sounds like we're gonna hear from Sean. So
okay. Sounds great. Yeah, I'll start. All right. Well, this is a lovely graphic that was made for an invented title for our group. So we're the Marine and Planetary Geophysics group. And we do a whole lot of different things, and so we thought we'd give you vignettes of the various things that we do. And I'll point out that while I'm advisor of everybody involved, I'm also co-advisor of almost everybody involved. So there's a lot of other people to thank, and so we have a big slide at the end that thanks all the other people involved in everybody's projects. Two people couldn't make it today, which are Carson and Soraya, so I'll actually present a slide or two for each of their sets of research. All right.
I'm gonna have to click on it, not just in the
like that instead. Oh yeah, because I'm not actually in the power.
Okay,
there we go. All right, so picture of everybody, those who happen to be at the last party at my house, and those who weren't. And our next picture will get everybody at the party, and it'll be fun. So that's most everybody here, including a postdoc who left from the group. So we have from left to right, Cyril, who's one of our co-advisor for several students, Eric, Carson, myself, Emma, Medha, Soraya, Mercedes, John, Enrique, Kylie, and Milo, who all are going to talk except for two of them. So I'm going to do it. Perfect. So I'm going to start as just a little bit of an introduction, and I have two slides, right? One, this is kind of all of our works on the marine side. So we both do coastal processes, tectonic processes, and glacial processes. All of these are really tied together by basically using some form of seismic stratigraphy or other geophysical stratigraphy, and often pairing this with drilling data. So for instance, a paper I put out this year is on a big mega slide in Alaska, in the Gulf of Alaska, that finally got published after many, many years. Kylie is going to tell us a little bit later about a reprocessing of my PhD geophysical data set from the Mendocino Triple Junction seismic experiment that's in progress. The lead PI on that is Brandon Shook, who's a former PhD student of ours, who's at Louisiana State now. Emma's going to give us a bit about Hikarangi, using EM data to look at subduction processes and fluids in particular, and volcaniclastic sediments. This is Carson Miller's work. This is a paper she put out last year, looking at the internal stratigraphy of these sandbanks to try to distinguish between what's a barrier island that's been preserved or just a modern Holocene sand sheet that's migrating around. And I'll show a bit more of hers in just a second. Enrique is going to give us a talk about the Texas mud blanket. This is a data set that we started with the field course, much like these data, and then now has expanded to a bunch of other data we've gotten a hold of, and we can do a much more detailed mapping. And it's leading into a new NSF proposal to go after the climate record buried in the mud blanket. John is going to talk to us about our recent Greenland work in West Greenland, looking at a couple of major glacier systems that are coming on the west side of Greenland, the seismic stratigraphy that we see here. So those are kind of those processes. And since Carson's not here, I'll do just one slide on her most recent work, which I thought was super cool. So she did all these analyses of various facies within the continental shelf in the area of these two major river valleys that are now that were incised and then filled in from the Trinity River and the Sabine River. These are those banks. And one of the things between her and some other students is that a whole bunch of locations were identified that represent a time when a shoreline was there. And so with dates and with the locations of, say, Shepherd Bank, when it was actually the shoreline, or this title in it when it was the shoreline, with those dates, there's this opportunity to say something about rates, right? And so this paper that she's working up for Nature actually is a huge rate change that's visible in the sea level rise during a time in the Holocene that is supposed to be a low sea level rise change. So what these probably are is not driven by sea level rise at all, but driven by sediment supply or subsidence, one of the other major factors. And it gives you a sense of the scale of potential rates in meters per year that are possible. And all these rates are between 2 and 8 times faster than any modern rates, even with all the anthropogenic additions that have happened, both in the positives and the negatives. So that's kind of a cool project. And then the other piece of this that's really interesting is a mapping of deposit thickness versus transgression rate and saying, what can you keep in the geologic record, right? So can you keep a flood tidal delta? Well, as long as it's thick enough, right? And the transgression rate is low enough, you hang on to your flood tidal delta. If you crank your transgression rate up, you're gonna wipe those out, right? If your transgression rate is really high, but your deposit thickness is lower, then it has to be in a preserved low. Like to keep a shore face is actually kind of hard to keep an overwash is possible if it gets in low, right? And a flood tidal delta outside of an inlet would have the same problem. It would have to be in a low, and so unless it's really thick, you probably lose it. So there's this sort of concept of geologic preservation that's also in that paper. Okay. Oh, no, this one, right? Yeah, okay, I will move to the planetary. So the other half of my group, I don't know if it's half, but something like that, works on planetary habitability, impact craters, and planetary exploration from geophysical methods. So we do things like the Chicxulub impact crater, which I just wrote a summary paper about this year. We also do things like exploration on the moon. So we're here from Medha Prakash about Schrodinger and a cool impact layer we think we found. We'll hear from, well, I'll give a bit about from Soraya Alfred's work on hydrothermal modeling at Chicxulub. We'll hear from Milo about radar on Mars. We'll hear from Eric about the water history of Mars using basically hydrologic models. I forgot I put that up there. This is actually not in our current group. This is somebody in Edinburgh. We'll leave it alone. And then Mercedes on surface reflectivity of the moon. So moon, Mars, and Earth. Okay, so quick snapshot about Soraya's work. What she's been doing is getting realistic geometries inside the Chicxulub crater, and then using all the data that we get from both impact crater models as well as drilling data in the peak ring to come up with maps of rock density, heat capacity, thermal conductivity, and so on, and then build all of this into a self-consistent hydrothermal model, which demonstrates the reason for the big convection cells that's set up inside these systems. And so this is a real step beyond the versions using hydrotherm and things like that, because it really identifies all the factors that go into the generation of flow. What we know is that there is extant thermophilic life living in the peak ring today. We didn't really know why it could still be there. We can demonstrate with this work, not only would we have kicked off a hydrothermal system 66 million years ago, but this creation of a permeability inversion and a porosity gradient will actually create a permanent convection cell. Very slow, but a persistent convection cell. And so we think that we still have a hydrothermal system there at a very, very low rate, and that's why life is still there. And so that's a pretty cool thing. So we're submitting a nature paper on that, actually. We'll see if any of these nature papers become nature papers, or they all go down to like GRL or something, which is the normal history. Okay, so that's it for me. I think we're gonna step over now to Enrique.
Do I go?
Up to you.
Yeah, I'll go.
Yeah, the controls are up here, but. Up to
So
you.
yeah, you gotta, I can drive it.
Yeah. Okay, so good afternoon, everybody. My name is Enrique Morales. I'm a senior here at the Jackson School. I'm in the undergrad honors program, and I'm doing my work with Sean, John, Carson, and my other committee member is Matt Malkowski. And like Sean mentioned earlier, we're working on the Texas mud blanket, specifically like the northern section of it. So just like brief introduction, I guess. I got introduced to geology when I was in 8th grade. My mom was my science teacher, and she kind of pushed me to join Geoforce, and that's how I'm here now. So this is our survey area. This is the data set that we're working with. The data was collected in 2022 by Aptim in collaboration with the Texas government. And so with this data set, we see a really nice spatially dense grid of seismic lines. Seismic lines, the short parallel lines are about 2 kilometers apart, and the short perpendicular lines are about 9 kilometers or so apart. And yeah, this is just, as you can see, it's a pretty big data set. It doesn't go very far offshore, but it does give us a really nice, dense grid to look at. And so this is just one of the lines that I've been interpreting so far. This top part here above the black is what we've identified as the Texas mud blanket. And as we were looking at this data set, there were a few things that we noticed. First thing we really wanted to look at were the seismic facies within. Then once we had those facies, we used those to determine different horizons that we could pick throughout the survey area. And those horizons gave us different units or packages to look at. And so this interpreted section down here just gives you a really good view of what that's been so far. So here we have H1, which is our deepest horizon. H2, H3, H4 denote different packages within, and H5 is our seafloor. And so the different, as I was talking about, those units are highlighted with those SU1 through SU4. And so this line specifically was chosen because it is able to show all of the horizon, all of the units at a good scale. And so some of the things that we've noticed with this data set, there's like 3 big observations that we've had so far. The first one being that you can see this kind of like stepping pattern within the units as you move to the southwest. The second one being that there's facies variations within the seismic units. So if you can see up here, up towards the northeast side, you see a lot more brighter reflections, and as you move to the southwest, it kind of dies out. And you might say, oh, well, maybe that's just, you're going deeper, you're losing your reflectivity. But if you stay at the same depth and move across, you can still see that same brightness. So that kind of takes that question out. So that leaves us with a little bit more questions about what's going on there. And then the third or the other observation that we have is we get a new extent for the Texas mud blanket. One of the big works that I've been looking at is a paper put out by Waite et al. 2011. And basically they had a big array of seismic lines basically running from about the mouth of the Colorado down to the mouth of the Rio Grande. And they were pretty spread out, didn't really have like a nice grid pattern to look at. And they used some reasoning to expand what their interpreted area of the mud blanket was. But with this data set, and because it's spatially dense, we're able to constrain a nice northern border for it. The next slide is just another one of our interpreted cross sections, and this just shows the short perpendicular. So yeah, this just highlights another version, another viewpoint for the mud blanket. And so with those horizons that I interpreted, went through and generated some services. And so it's a little hard to make out. I'll work on that. I'll work on this figure a little bit more. But up here you can see that H5 is our seafloor, just for some guidelines. H1 is what we've identified and interpreted as our transgressive revenement. And H2 through H4 are those units that I was talking about earlier. So you can see here that as we move through time, that these different units are moving closer or moving towards the southwest. It shows that stepping pattern as I was talking about earlier. And so, yeah, this is just part of the work that we're doing, generating some isopacks now, and I'll be presenting this work on Monday.
Understood. Yeah, excellent. Thank you. Yeah.
Hello, everybody. I'm John Amendola. I'm a current PhD student, obviously working with Sean here, and then my other co-advisor is John Goff. And so I was working as part of the Terminus project to Central West Greenland this past summer. My side of work is mostly the geophysical side of things. I got my BS in earth science with emphasis in geology at UCSB, where most of my work was mostly looking at sediment cores and analyzing tsunami deposits in northern England. Doing a bit of a pivot now to focus more on glaciology, as well as just kind of using geophysical tools, which is a completely new area for me. Primary interests are geomorphology, glacial geology, and again, still sedimentology. But if you'd like to move forward. Part of the Terminus project, the main point of it is to just broadly understand, what drives glacier stability in tidewater glacier systems. What is the role of sediment in driving, the stability as well. My interests in that are kind of understanding, right, to the erosion rates of these glaciers, how these moraines are being built, and then also just broadly, what is the entire picture of the sediment budget here? This figure on the right here is just kind of broadly showing why we think that moraines can actually cause stability in the Taiwan Glacier. You know, as you have sediment coming in over the summer and winter periods, you're creating this moraine and developing essentially a shield at the base that's decreasing the terminus exposure in the summer and the winter, preventing kind of this warmer ocean water from melting the terminus space. There's some other things as well, but right, that's one of the principles that we're looking at. Over here on the left is kind of broadly this figure from Jaeger and Kopis, which is a great review paper of just glacial cryosphere sedimentation and erosion. And so they collated a bunch of erosion rates from Alaskan, Patagonian, POW, Taiwan glaciers to understand, you know, where do all these things compare. And then in the red, this is me kind of altering and butchering the figure and throwing in some work from Walter Kennedy, who's actually the UTIG speaker this week, so I think I'll see your talk. But so just kind of understanding, like, so Jakobshavn is the fastest flowing glacier in the and it has an erosion rate, you know, in several orders of magnitude lower than anything we see in Alaska or Patagonia. And so why is that, right? And so we want to compare our glaciers, CAS and KSS, to, you know, what we see there. Broadly, this is kind of just an overall view of the survey area and the coverage. We had chirp seismic, multi-channel seismic reflection, and multi-beam bathymetry surveys, as well as a bunch of other operations that I was only part of. As you can see up top, we have KAS, which is a much larger glacier, considering more sediment flux and ice flux, as well as much more stable into the Saleh area the past 40 or so years. Where we have KSS in the south, considerably less sediment, less ice, and has retreated around 2 to 3 kilometers in the past 10 years. And then again, you can kind of see our just spaghetti pile of survey lines. It's not a very organized grid, but that's what happens when you have to dodge icebergs. Right, yeah. Right, so this is kind of actually, sorry, if you go back one more, I forgot that whole part. So you see kind of here in CAS and here in KSS, which might be able to see a little bit better. There's two kind of proglacial plateaus that are formed from what we believe is kind of a little ice age moraine retreat system. Little ice age probably terminated somewhere in Greenland, or in Greenland somewhere between like 1850 and 1900 AD or CE. And so now if we go forward, this is what that the side profile of this kind of paleomoraine system is. This is in CAS. And so what we're really interested in is kind of analyzing, you know, what is represented by the internal structure and the internal structure within this moraine. What does that tell us about how these moraines are formed? As well as, you know, what does all the sediment above this horizon represent for the erosion rates since, you know, the little ice age review. And then in this next one, we have KSS, which, you know, this surface, again, we see this moraine here, but we have practically a lack of any sort of sediments on top of it. So this is going to be really interesting to kind of analyze what's this surface looks like actually. Like what do these moraines look like when you pull the ice back and just have this stuff exposed? Yeah, and so this is also just kind of showing how KSS has retreated in the past 20 some 40 some years.
Yeah. Excellent. Cool. Kylie.
Hey everybody, I'm Kylie. I'm a junior in geophysics major in Jackson School. I'm also in the honors program. My thesis is about seismic data reprocessing and interpretation of the Mendocino Triple Junction and Southern Cascadia subduction zone accretion wedge. So, yeah. So where is this? This is off the coast of Northern California. These are both from Brandon, if you guys know him. This is from the KC-21 project. They did all of these red lines up in Northern Cascadia, pretty much from Oregon all the way up to Vancouver. This turquoise box right here, these are my lines, and by my lines, I mean Sean's lines, because he did these for his PhD in 1994. So, not to call you yeah, so these are all of our lines. They kind of go over some of the faults in the area. This is over the transform fault. The other two figures I'm going to show you are from line 6, but yeah, this is where all the lines are. So this is not to dog on you anymore. This is Sean's data from, this is when he processed it in 1998. All of MTJ6, it starts, kind of in the middle of the basement. We call this the seduction section. But I just wanted to show you the old data so that when we flip to the new data, which we're not done processing, it looks really good.
Yeah.
So this is all of MTJ6. Sean's box was like here to here. So you can see we still have some work to do. We still have a multiple at the bottom. But so far we've had a lot of issues with the data. We had to add headers to all of the data, which is like GPS. What else did we have to do? We had to fill in all the missing shots and channels, which was a lot. But we did a mute, or not a mute all over, we did a denoise, we muted above the seafloor, and this is the first line that I picked velocities on. Yay! You can see the basement here, which looks really good. Hopefully, once we get rid of the multiple, we'll be able to see it all the way through.
You can see it on the far right, it's coming out.
You can see it, I don't. But I think that this looks really good, so, yeah. There's one more slide.
One more. All right.
Yeah, so we just have to finish with picking velocities. This is all in Reveal. If anybody wants to learn how to use that, I'm like making a guide, so. Yeah, but we have to finish picking velocities, finish processing. I think this week we're doing a de-alias, a designature, a debubble, all kinds of fun stuff.
That's all right.
And yes, so hopefully soon we can look at the geology.
Hey.
My name is Emma Parker. I got my my undergraduate in mathematics and then my master's degree in hydrographic sciences. So, I like technical things and I like math and I like making maps, but I also like figuring out what's underneath them. And that's what I'm doing here in my PhD is characterization and specifically targeting, problems and, earth processes that will target new blue economy initiatives. So things that have, these exploration aspects to them. And that really brings me to these tectonic margins and looking at geohazards and resource exploration. So I'll be reprocessing data from the Northern Hickory subduction zone, which is in New Zealand. And this is where a thickened portion of the Pacific plate is subducting beneath the Australian plate, and it has very complex lithology. And there are a lot of really interesting processes that are going on here for geohazards. It's also, especially with everything going on right now, important to figure out new ways of combining existing data sets to maybe ask better questions, or at least be able to, generate more targeted future initiatives. So just going back to this, I'll be using electromagnetic data sets as my sort of primary data set because it is sensitive to the kind of processes that I want to look at, which have to do with fluids and fluid mechanisms in 4ARC here at the subduction zone. So here, lots of high resolution data sets, including a 3D seismic volume. This was published by Nathan Baines in 2023. There's an EM line extending outside of this volume, but they are co-located and also co-located with IODP drill sites. So we have in situ collections, we have extensive seismic data, both 2D and 3D, and EM data in both magnetotellurics, which is passive, and active source, which is controlled source electromagnetic marine data. So I really want to go through and figure out ways of constraining the EM data to change my inversion from, well, what is the electrical resistivity of the Earth to what is the electrical resistivity of the seismically constrained region. So doing that, this is sort of a, sorry, the coloring on this is awful, broad strokes idea of kind of what we expect the lithology to look like. And as you can see,
there's this layer on the very top of the volcanic basement. And that is associated with this smectite rich layer, so altered volcaniclasts. And this is thought to really change that fluid budget in the 4-arc region. And it may influence ultimately the stress state as it subducts, as these pockets come in. So what I'm doing is picking the bottom of that layer because I think it's associated with a jump in conductivity. And picking a constraint, it's really important to choose one that is associated with the data set and what it's sensitive to. And so EM data is sensitive to conductive phases of fluids, so pore fluids and not mineral bound fluids. So I have picked that layer and ran one constraint model. So here's just saying that again, validated it with in situ measurements. I guess really brief, I put this in so you guys know a little bit more about EM, my speed overview. You have time series data sets, you do a Fourier transform, you look at the data, MT, you get response functions, and then you run that into an inversion model. And what I was doing, you can't see it because it's under Zoom, but this is where I'm putting in my constraints. So I put it in prior to the inversion, and it's like an extra structure. And essentially what it does is it penalizes this regularization inside of my inversion. And for today's purposes, I ran it through my preferred model as of right now, through Archie's law, which is a empirical relationship that takes you from resistivity to porosity, just so you can get some broad strokes idea of what this changed. And if you get to the next one, so using just some basic values that have been used in the past by previously published data, you can see that here's the unconstrained version where it's just, you know, the inversion is just ran and you have a lot of these smoothing. And this is what happens when I place a constraint on it. So it takes all of those conductive anomalies that were originally being smoothed below, and it places them all in that 4-arc region. And so it tells us that, yes, there is definitely porosity, but there's also patchy porosity. And I hope to really, in the future, if you hit that, refine this constraining boundary, maybe incorporate more constraints as I go through the seismic data, and then maybe eventually create more robust models from porosity, resistivity to porosity to really, I guess, refine the story. Yes. Yeah.
Yeah.
Among other things. So, yeah, that's all I have for today.
Hey. Hello, everybody. I'm Medha. I use she, her pronouns. I'm a second year PhD student here at UTIG because I am here. I've done my Bachelor's of Science in Environmental Sciences and Statistics at UVA. I feel like my research topics have hopped around a decent amount since I started, but what I'm here to talk to you about today is like my first chapter on thinking about impact processes on the moon, specifically in Schrodinger Basin, but I'm happy to talk about any of these interests later if you guys are interested. And luckily I have more than a few seconds, but if I were to summarize my entire first chapter in a few seconds, it would be this. If you guys have seen any of my presentations at YouTube. So next slide. So basically, I'm interested in answering a few questions in Schrodinger using a bunch of different types of remote sensing data. So firstly, I want to look at stratigraphy, specifically looking at deep cutting structural features, which Sean and I came up with the wording for today, in the basin, such as volcanic vents, Robbins, recent impact craters that cut like kilometers deep into the surface. And I'm using topographic data derived from the Lunar Orbiter Laser Altimeter and really high resolution imagery from that same mission. My next question that I'm also like to think about is how do depositional mechanisms of materials produced by impacts differ between the Earth and the Moon? Are they like broadly similar across like planetary bodies that are rocky? Are there some fundamental differences? That's what I'm interested in thinking about. And also, just generally, are there any major implications of this, which there probably are, and will be, for the geology of future missions? So I'm gonna hop right into it. That's Schrodinger Basin. So the next slide. Basin. Oh man. Okay. Well, I forgot about my animations for the little text boxes, but that'll be okay. So why don't we click the first one? Oh shoot! No, wait, go back.
It's covered by Zoom. It popped up. It's
Okay.
Popped up, it's up.
I think my first text box was that this material that I've been mapping is a really high albedo cliff-forming material. So in this image over here, you can see like there's this bright layer that is beneath this really dark material. It also has steeper slopes than that dark material and the material below it. And so we're like, oh, is there other deposits of this material throughout the basin? And so this map on the right shows that yes, there in fact is. All these green and white dots basically show where we believe we've identified this deposit. And so it shows that's very pervasive. And I think the other text box was saying that it was on the magnitude of 125 meters thick when you average it all out. So next. And then
It's also underneath.
yes,
There we go.
oh, that's not one. The other thing that I was gonna say is that the slopes that are reached across the profiles of these outcrops are up to like 53 degrees. So that's like a very coherent rock layer. Like that's like beyond the angle of repose. So just like a pile of sediment on the moon. You can't like, it's about 35 degrees. So this is showing that it's a coherent rock layer. Next. This is an example image of an outcrop atop the peak ring, which is like a kilometers high feature in Schrodinger. And so you can see that there are these sort of strata that sort of like pinch up atop like the topography, and they form this sort of onlapping geography. So that implies that this material somehow climbed up that topography, perhaps implying a lateral flow mechanism. And then additionally, the different colored dots are showing the different sort of textures that we've observed for this material. So you can see that it is higher albedo compared to the surrounding lunar regolith, but you can see that there's kind of a more rubbly coherent one, and then a more sort of powdery one. You might see some boulder falls from it, and you can see that they're not really like restricted to certain grabens. You kind of find examples of both in all the grabens. Okay, and then next slide. So the implications of finding a layer like this, which we believe to be like analogous to a terrestrial sagebed, which is an impact breccia, is one thinking about how this flow mechanism can actually happen on the moon. That's something that we've been grappling with, and it's like, yeah, it's just interesting to think about, because normally you think about some fluid driving it, and it's like there's no fluid on the moon. So there's that. Next is like thinking about, can we expect like these impact breccia deposits to be elsewhere on the moon? Are they just restricted to really large old impact basins? What about like smaller, more recent craters? Could we find these over there? So that's something also super interesting. This material on Earth is used to construct towns. So this could be a potentially useful resource for in-situ resource utilization. And so where can we access it in the basin? Because you probably don't want to drive a rover down a kilometer deep graben. That'd be a bad decision. So thinking about where we can actually access that sort of material is interesting. And some future work that I'm hoping to do with lunar stuff is thinking about the actual crustal composition of a pre-existing, like there was a really large impact that happened like a few 100 million years ago before Schrodinger that kind of changed the composition of the lunar crust of like an entire region of the moon around the South Pole called the South Pole Aitken. And basically, you can look at crystalline exposures in Schrodinger and other like more recent impact craters to think about what the actual crustal column and like pre-existing stratigraphy looked like before the Schrodinger impact. And then very importantly, I'm also very interested in thinking about if this material is a viable material to make test ports on the moon. If you guys came to previous discussion hours, you would know what I'm talking about. So come to discussion hour. Yeah, that's me.
That's
I'm Mercedes Jordan. I think most of you guys know me, but maybe not everybody. So I finished my bachelor's in December. Before that, I was working with John and Cyril on the same work with the honors research program. And I'll start my master's here in August. And I'm currently working as a research, like, what is it? Research engineering scientist associate. again, advised by Sean and Cyril. And our goal with this work is to both map lunar radar sounder surface reflectivity, which is kind of, we've done a lot of that already, but also explore the drivers behind the heterogeneities in the reflectance that we're seeing. And I think, like, ultimately the goal is to use this work to inform the planetary science community on the utility of radar reflectometry for both resource exploration and for geologic interpretation. I think that there's a lot of potential with data like this that hasn't really been tapped into yet. I did forget to kind of put in something about what the lunar radar sounder surface reflectivity like is. This is a data set. So we've extracted surface echoes. So these are like the first echoes back to the sensor. But the lunar radar sounder was on board the Kaguya mission. This was a satellite that orbited the moon between 2007 and 2008. And so it collected a global radar data set. And that's the only one that we have like it for the moon. And so looking at the second little subset there, I wanted to show you guys a normalized map of surface reflectivity. This is on the lunar near side. This is kind of the region that I'm most interested in at the moment, specifically the lunar maria. So in the little image on the left, that's going to be the low albedo kind of terrain, like the main and the moon. And then in my map, that's the blue terrain. So there's kind of a lot of heterogeneity here. We can see that there's primarily two facies. Maybe I can map more, but I don't really want to at the moment. It's a lot of work. But yeah, we have a bright facies and a kind of this medium facies with different power distributions. And so my goal is to kind of explain what is driving this heterogeneity or this variability in radar behavior. And hopefully you can kind of see it, but my kind of thinking is that surface reflectivity may be a proxy for certain material properties and or it can probe the structure of the near lunar surface. And the reason that I think that that's possible is because radar reflections are generated and their strength is determined by the permittivity gradient. And permittivity is just a material property that's related to like density, porosity. It's related to all these other material properties. And so we can kind of connect this power of the radar reflections to these materials and what they look like and what they are. And so in this, in 3, you can see kind of one of the big assumptions that we're making in this work, and that's that we have this kind of consistent structure that we can say is consistent throughout all of the lunar maria. And so you have vacuum, you have your radar wave that's going to propagate through this vacuum down to the surface, and then a radar reflection is going to be generated at this interface between the vacuum and the Mare regolith. The Mare regolith being this unconsolidated material, low density, low permittivity, and there's a gradient between the vacuum and that regolith. So that's going to generate a reflection. And then you're going to propagate through the regolith, and you're going to generate another reflection at this regolith Mare basalt interface, with the Mare basalt being higher density, higher permittivity, much higher than the regolith, and so you're going to generate another reflection because you have that permittivity gradient. And so that's kind of the big assumption that we're making. And so we can kind of say maybe the thickness of the regolith is going to affect our power, or maybe the composition of the Mare basalt underneath the regolith is going to affect the power. And so we want to kind of test all of these different parameters, all these different things that affect radar against our surface reflectivity to determine what it's most sensitive to. And so in the 4th little subset, I showed like super recent work. I made this plot on Friday, so we haven't like really looked at it too much. This is a heat map, and we're looking at the correlation coefficients, the R values, between the surface reflectivity and all the other parameters with each other. But against composition, TiO2 and FeO, weight percent, Mare basalt age, RMS height and slope, which are like roughness products. Radar is super sensitive to roughness, and so we're looking at that as well. And then also this regolith thickness. And yeah, so we're just kind of looking at all of these correlation coefficients and trying to determine what is surface reflectivity most sensitive to. From this right now, it looks like RMS slope, which is different than what we were thinking in the past. So we have a lot to talk about in a minute. I think Cyril is comfortable with it, so we'll see. But yeah, a lot of collinearity, not really sure how to handle it. So I definitely wanted to pull this up, and if anybody has like any advice or any ideas for us, yeah, let us know.
Next slide's design.
Yeah.
Oh, no.
So, yeah, that was
Cool. Milo.
Hi, I'm Milo. I'm a junior geophysics major, and I'm currently working as an undergraduate research assistant under Soraya and Gulick. And I'm currently working with them and looking at remote sensing data to find terrains on Mars which could serve as potential analogs for the bright reflector beneath the Martian SPLD. So in 2018, a bright radar basal radar reflection was found under the Martian SPLD roughly around here. It was initially used as evidence for either, at the most extreme case, a subglacial lake or just hydrous minerals, but the conditions under the modern SPLD make that incredibly unlikely, leaving two possibilities. One, that our understanding of the superficial layer covering it is incomplete, giving us a basal reflectivity that's artificially inflated, or there are other terrains on Mars that could serve as a potential analog for it. Cyril Grima did a paper back in 2022, imagining if Mars was covered in a roughly a kilometer and a half ice sheet similar to that underneath the Martian SPLD, and use the surface reflectivity from Marsis in order to calculate the hypothetical basal reflectivity we would have. And there seem to be locations elsewhere on Mars with theoretical basal reflectivity above 2.5 dB, which is what was observed under the Martian SPLD, and they can provide potential explanations for what it might have been. Right. And here's the results that process gave from Cyril's paper. Here you can see regions that are above 2.5 dB and can serve as potential analogs, with the rest in red that don't really seem to be that bright. Right, so my goal up until now has been primarily to sort through this data to find regions which are consistently bright. And so far I've devised two methods which seem to provide decent results. One method, I took the raw data points above 2.5 dB and then filtered them based off of the amount of bright neighbors they've had in a different orbit, just on the possibility that there could have been an issue along one specific orbit or specific area artificially inflating the brightness of a region. And I put the limit of what would be considered a neighbor at about 0.7 degrees. This is a little arbitrary as you can increase it or decrease it, but this seemed to be the best compromise between removing noise and preserving the large bright structures. It also may have introduced a horizontal bias, and it still seems that you're moving some reliable points. The second method I devised was turning the map into a 3 degree by 3 degree grid and then taking the ratio of the bright points over all the points, which seemed to provide a decent overview as well, with the regions with the major region and Athabascus Vallis being the most obvious here. From these maps, I found the primary areas of interest to be Athabascus Vallis, Dalmatia Planum, Lune Palus, and the region here south of Tharsis Montes, with the region west of Palus Basin here and Citrus Major Planum being secondary areas of interest. So far, there seems to be a correlation between bright regions and high epithermal neutron emission, which could just be a indirect relation as igneous rocks tend to be hydrogen poor. And most bright regions seem to also be igneous in origin, which we can see here. It also seems to be correlated with low surface roughness, which makes sense since that would increase the coherent component.
That's it. Okay, good. All right, Eric. Last one.
Hey everyone, my name's Eric. In my terminal stage of PhD, I'm just too exhausted with the intro slide, obviously. So I'll do that now. I've been at HT for 9 years. I was an undergrad here. I'm advised by Sean, Mark Hessa, and a really strong assist from Tim Gouch, who's like my third advisor essentially. What I like, I play hockey, rep hockey, a bunch of kids, and in my spare time, I like to think a lot about the climate of early Mars and what some of those drivers have been. So primarily I'm computational geophysicist. I model and I use remote sensing data to inform these models. So what I do is I take NGS data, MOLA, laser altimetry, the original OLA, by the way. And then what they did is produce a topographic map of Mars. Here you can see on the right, where anything in blue is low, red is high, red and whites are in higher. I use that to inform my model. But to understand a little bit about this, we're gonna use the car map of a fluvial history of Mars. Mars has like two sides to it, both topographically and temporally. So first, we're gonna talk about the topographic part. And so what happened early on in Mars history, this is back in Hadean time of Earth. The oldest thing on Mars is this dichotomy up in the north. The crust is about half as thick. You have a 4 kilometer sharp drop off. It's basically where the putative ocean would have been. It's one of the larger basins on Mars. You also have these two impact basins, Ardra and Hellas. They're equivalent to Oriental and things like that. They were late heavy bombardment aged on the moon. And so they become really big topographic drivers on these models. Temporally though, we have basically two time periods, when Mars was wet and when Mars wasn't. There's some little interplay between the two, but the good thing is that it desiccated and dried out fairly early, and it retained basically 4 billion year old crust. And so we can look back and look at geomorphic signatures from 4 billion years ago when Mars was wet. And so what we have here, so in the valley network area is the main time that I am concerned with. I would truncate that little timeline a little more to about 300 million years or so. But this isn't the oldest trains on Mars circled there. I'd like you to remember that, because these next models I'm going to show you that I did not circle them, and that's going to be the important spot. But what you find there is these weakly integrated fluvial systems. Some of them can be somewhat more integrated, up to like Strahler 5 or 6, dendritic type stuff. Next. The valley networks themselves are these in-cut networks. On the left, you see the Colorado River, the Grand Canyon. On the right, you see a valley network on Mars. They're deeply incised canyons on the surface of Mars, can run for tens of thousands of kilometers, kilometers deep. Next. You also have clear evidence of water just all over the planet. Here in Meridian Planum, you see this is an endurance crater. This was from Opportunity River, which was sedimentary rocks that were laid down in water. Next. Over here we have Curiosity River. This is a Gale crater, found a fluvial cluster environment there, which had rounded cobbles, imbricated stuff, all clear signs of surface water activity. This would be where Perseverance crater is at, or Rover's at now in Jezero crater. It's the delta where Dr. Gauss could show that was clearly formed in a standing body of water. So you have all of these signs of surface water, but all the climate models on Mars cannot reproduce running surface water. So this is incongruent with what drove these climates and what produced these obvious signs of superficial water. Next. So what I did is I took a model, I made I did all backstory. I put it all on a globe. So you have, your operators are all in spherical. Put it in, I can take and cut out parts of my domain. I have dynamic domain, so I can literally pull out set boundary conditions within my model. So that way I can represent standing bodies of water, which I've never done before. And then what I do is I take from 45 to 45 and I recharge on that band. For this model is homogeneous, but later on we've changed all that. What I did here is I recharge it at 0.01 millimeters per year. Remember, that is recharge, not precipitation. There's a partitioning that happens between runoff and recharge. The conductivity, we can argue all day about, but I chose that value, and I'll tell you why it really doesn't matter later on. And here at 0.01, what you get is something reasonable. You see, we get that in Meridiani where you saw the layered deposits. Everywhere else, the water table's below the ground. I should probably play my bar. I take the model output topography and I subtract the two. So where the groundwater is above topography, it's blue. Where it's below, it's red. White is right at surface. So this is acceptable. It'd be a perfectly good parameter space. So we try to play this game next. That's at 0.03. So 0.01 to 0.03, you're getting pretty close to exactly what you see on Mars, where you see these, there's something called light layer deposits there in Meridiani. And then next, so 0.1, and you're flooding out 60% of the surface, right? So that's pretty acceptable. Next. So then comparing it now, y-axis, we have percent experiencing upwelling, where water's reaching the surface. On the bottom, we have log scale for recharge in millimeters per year. Our three scenarios that I just showed you are plotted in the panel A, panel B, panel C. And across the top, you have precipitation, which is these modeling that do climate models essentially. Snow and ice, which is like basal melt from glaciers, and direct recharge would be actual numeric modeling of groundwater that's been done before me. They're all very low compared to all these guys, right? So what does that mean? So we'll start with this out from all this work. I didn't think this was a very valuable thing to put in my first paper, but I'm like, so you have advisors for a reason, I'll tell you that. So like this R over K value, just from non-dimensionalizing, we did some like analytic work that we assumed some really hard boundary conditions and made it really like step functioning and all this stuff. And when you non-dimensionalize, out pop that value, which is recharge over conductivity, since they're both in meters per time, length scale per time, it's not dimensional, it comes out 10 to the 5th, negative 5th. And so what explains some of these things, maybe Mars didn't have a lot of water where, you just basically ran out of, stuff to evaporate before your climate cycle ended. Or maybe the transient response was slower, so next. So I'm sorry.
Oh, sorry.
So, you're recharging and your water table is going up, but then next, you turn off the recharge, it goes down, and the recharge maybe wasn't long enough to actually flood out the surface, before it stopped again. And so that's what we want to do with our second paper. So long story short, the next slide is I've now completely redone a transient model. It has moving shorelines that move when I turn a recharge on and off. It has a transient, solver. It storativity issues, the level of your aquifer matters in, to how much things go, and connectivity varies with where your aquifer height's at. All the bells and whistles one might want, variable time steps. I ran 200 miles now, I'm probably on my way to 400. And so you can see there 500, I've got basically this, parameter space that says 500 on, then 1 million, 5 million, and 10 million off. 5,000 on, 1 million, 5 million, 10 million. 10,000 on and 50,000 on that same parameter shape, right? And when you plot the R over K average, like you now take, it's not just recharge, it's not constant, it becomes an integrated value over time. And when you integrate that over time and still look at that ratio, it still centers right about on 10 to the negative fifth. So regardless of what you do through time, as long as when you integrate over time, it still has to come back to that steady state, which gives us the next one. A powerful tool for looking at like what geomorphologists and things like that think, for, if you need X amount of water to cut this canyon, because, you think, whatever, erosion incision rates would require this or that, then you can take and partition off, some amount for groundwater. And it will tell you whether that's reasonable over geologic time, or where you would have flooded out things and produced basically groundwater induced landforms that you don't see on Mars. Excellent.
Excellent, thank you, everybody. But yeah, now we've got time for questions for anybody.
Oh, whoa, right. I forgot. Yeah. I spent so long at this, I totally forgot this. So I tried to like put all the faces up of everybody on all folks committees, co-advisors and so on, as well as all the incredible people here at UTIG that make it all possible to do all this work that we do. So hopefully you find your face like that. Anyway, questions? Or anyone? Yeah.
I have a question for Mercedes and Milo. Both you guys are looking at characteristics of the surface with radar, and I was wondering if if there was another radar survey or other data that was going perpendicular to the lines that you guys are getting from the satellite coming around the planet, that you could observe some anisotropy in what, like the surface characteristics that you're looking at.
I think, well, the answer for me is no. We only have one satellite radar data set. There's some, much shorter, or much lower or higher frequency, lander data sets. But no. And then I guess, I don't know, Milo, I don't think so.
I don't think there are any, but for Marsis, there are different bands, like I look primarily at the 4 megahertz one, and looking at it as micro would be different as well.
Do you think anisotropy would be a useful metric at all for you guys, or is it something you not as important?
I'm sorry.
Do you think anisotropy in what you're seeing would be a useful metric, or?
I'm honestly not certain. I think we should talk about that, but I think I forgot about mini RF as well. There is mini RF, but it's such a different frequency that it's not really useful for us, but we should talk about it.
Sure.
Yeah.
Yeah, there's not a lot of anisotropic features that we sensitive to, plus it's an area looking, those are media looking radars.
Yeah.
And so roughness might produce some kind of depolarization from anisotropy, but it's like that. At this moving angle, the depolarization term, the relativity is very small, if not non-existent. You do increase the impact of the signal from anisotropy when you start to look off that year. The most inspiring.
Which would be more effective on like mini RF. Other questions? Yeah,
So along the same line, if you compare your data with, P-band radar,
No, we haven't. P-bands, what's that frequency?
like 450 megahertz roughly,
Um,
it will be Earth-based. So,
Yeah.
so only looking at the Earth-facing side of the moon.
Yeah.
But it will penetrate deeper, so maybe still what like the order of magnitude higher frequency, but maybe more sensitive to the same scale of topography.
Yes, absolutely, in a different way, yes. And we are starting thinking in one of those lines to compare the activity at the moon about 4 megahertz. With the RS, with the one from Sharad at 20 megahertz on Mars, right? Because you have some kind of terrains with similar wages, for example, volcanic terrains, and we are trying to look at the different behavior, the similarities in relative behaviors between those two frequencies.
Yeah, so we're using a data set that uses that Earth-based radar. But it's essentially they inverted for regular thickness, so we're using those products, but that's the only way that we've integrated that so far. Yeah, but.
I think a bigger picture question,
Yeah.
that I guess nominally for Sean, but anyone could pitch in on. Given all the different subfields, or fields in and of themselves, how do you guys run lab meetings? And how often, in relation to that maybe, how often do breakthroughs kind of cross-pollinate and come from the different areas?
So we run separate lab meetings, like the planetary group meets independently from, and then subsets within it meets independently from the marine side of the shop. I do think there are breakthroughs that come from observational data sets across. So we learn something about the way to think about what geophysics is sensitive to, of whether it's seismic or radar, just we get some insights from that then cross over in some interesting ways. And also physical properties of things. We, spend a lot of time thinking about physical properties of Earth materials and planetary materials at all these different scales. And I think we learn a lot from these different settings. When we drilled things and thought about what really is the important factors and what controls it. And then we go to a place where we don't have the samples, it's actually can be really, really insightful. So that would be my way to answer that. If anybody has any other comments.
Your answer is Sean is the busiest person.
Well, I think there's a lot of synergy, because like even Soraya's work on so when I told her I could cut out like my cells and then make a lake there, like that removes what Sean really cares about, which is the greater part, the hydrothermal system. But like if you want Soraya's work to think about how long a hydrothermal system lasts, especially if it's not inundated initially, you need a groundwater flow on a regional scale to put as a boundary condition into that house. Like Soraya's and my work go hand in hand and have all kinds of ability to cut implications, past that. So they kind of like work part and parcel.
I feel like my future work in my thesis is gonna be looking at like spectroscopy and like the spectroscopy of like the sort of like materials that are produced by like the systems that Soraya is like modeling. And so like I'm gonna be gathering that same data on like a new field site, which I recently got funded for like this summer, but like also I'll be gathering that same type of data on the same Chicxulub cores that were drilled that informs Soraya's model. And so that will be like super interesting to see as well. Yeah.
Also a big picture question for Sean, and by studying the crater on Earth, what is the big picture to study the craters on other planets?
So I think in general, the comparative planetology way of thinking is super useful, whether it's volcanic processes or impact processes, just going to a place where we get much more information because we have the detailed subsurface information like we get on Earth. And the thinking about what we have on another planet, like say Schrodinger, where we have this beautiful surface, better exposed surface, better information about from that perspective, but we don't know the subsurface very well. You can kind of go back and forth with these two sets of appreciation and interpret each one a little more detailed because you have the better version of an appreciation of a structure on the other planet. And it's actually really about data availability, right? But then you also have to think about how different is it? This is what Medha was getting at. How different is it when there's an atmosphere for some of these processes when there's not an atmosphere? And surprisingly, what we're seeing so far is doesn't look very different. So now you got to ask the question, why? you know, how is it we can create, you know, say like a ground hugging flow in the middle of an impact process in a place where you have a fluid of an atmosphere, and a place where you don't. Right, those are cool problems to think about.
I know I'm part of the group, but I do have a question.
Goes back to what you're saying is, so Eric has this model that looks at canyons that were formed underwater, right? There was one of them was below sea level, is that?
No, so there's only a few that show signs of international groundwater, so that's like a constraint, is if the groundwater is above it, I can throw on the backside, because it will show sapping, geomorphology, and some mineralogy associated with like water coming up and a lot of water up in there.
Okay,
So he's actually looking at the groundwater had to just get to it in order for it to be down cutting. And if
Okay.
it actually floods it too much, it doesn't make sense anymore. And so there's a limit to how much water for the valley foaming network era of Mars to have cut the canyons that you observed.
so none of them would be like the offshore canyons that we see here.
No.
Okay.
And in fact, when you go to what they think is an ocean, it's all filled in, it's all flat, so we don't even have a morphology of anything you would think of as a marine morphology. If it was.
I don't think it really was.
Yeah, it may not have.
I'm shifted, it was like my cold narrative.
Well, I guess, how would studying, I guess, marine canyons on Earth help you, I guess, support that evidence?
How does?
And like
how it-
morphology.
geomorphology?
Yeah, like Earth
So
analogs. that-
there's
talking
some
about craters.
there's some arguments about like interior head wall erosion and how that works. You also see clean places that they leave groundwater fed, like other lakes, and they have different mineralogies there, and you just don't see that in the upper reaches. And so that's why that's supported. I personally, I like the paleontology thing a lot, but I think Mars does not work.
That's
Yeah.
very fair.
I don't think the groundwater was ever really connected to topography, but for the vast majority, it's like, what does that mean for? You know, we at one point probably had a global groundwater catchment, that it was all going down from the base basin. Like just that being formed, there's so much.
Once you made a
storage
giant
space
impact,
in there,
everything flowed.
that there was no more groundwater divides, that it was just the whole planet was going there.
It's pretty different.
So Earth analogs are,
Not always.
Well, no, so but I can say,
Nice.
the other thing is that you can see the influence of groundwater on morphology on Earth, and when you don't see it on Mars, it tells you something about it.
Yeah, that's the way to go. All right,